All right, class, as we continue through lesson 3-1, we want to see the application of the exponential function as it relates to finances, and in particular, using compound interest. And so we are given a foundational formula here, A, where that is the account balance, is equal to P, which is the amount of the principal. Now remember, the principal is the amount of money that's originally invested. Say like I have $5,000 that I want to go to a bank and invest. What is it going to look like? What's the account balance going to be after T years, the number of times N that it is compounded in years, and the rate, which is always in decimal form, R. And so this formula, we're not going to try to derive this formula, just simply using it right now. What happens if interest is compounded semi-annually? And that means N is equal to 2. And it's the number of times in years, meaning during a year, I should say there. So if it's semi-annual, it's every 6 months. Don't do 6 because it's twice per year. And in this particular scenario, we're given a principal amount of $300 and it's invested at a 6% interest rate. But do not put 6 in there. You will get an extremely large number. You have to put that in decimal form. And so that is 0.06 and the term is for 20 years. And really at this point, it's all about substitution and proper math work, proper calculator work, I should say. So we plug in the 0.06 for the R, 2 because it's compounded semi-annually. The 2 again, notice that the N is here in 2 places, and we multiply the N times the number of years it's going to be invested. And in this particular case, we get $978.61. For B, what if it's monthly? Well, that's every month, so there's 12 months in a year, so N would equal 12. In this case, we have $300, same interest rate, same overall term, but if it's compounded monthly, the account balance moves to $993.06. Well, what about daily? Well, that's 365 days in a year. We're not considering a leap year right now, just a normal year. And again, you can see the math. You plug in the 365 for N, and it ever so slightly increases the account balance. Well, go ahead and look at the guided practice problem. They give you P of 1,000 years, the principal, a new rate, and term. And again, I'm not going to work through these. Semi-annual is twice per year. Quarterly, that is 4 times a year. And then, of course, daily is 365. So you should be able to work through these and crunch through the numbers and get these 3 respective account balances. Well, what about example 5? This moves more in line with our particular lesson dealing with the exponential function, and in particular dealing with this natural base. And so what if the compounded interest, or what if the interest, I should say, is compounded continuously? Well, then we have a new formula. And in this case, we have the account balance for A. P is the principal. We have our natural base, and we're going to raise the natural base to the product of R and T. And so in this case, now don't think of this as a variable. This is a constant. It is represented by E, and you can simply execute the math and get $996.04. So a continuously compounded interest actually lifts interest just a little bit more than even daily. And you can pause the video and try the guided practice number 5 problem. Again, here we've not worried about trying to derive these formulas. We are simply using them. Now, for example 6, we want to model using exponential growth or decay. Now, when you think of growth, you think of it increasing in value. Decay, well, it is decreasing in value or worth. And so what about if we have some funds that are growing at a rate of 1.42% annually? So that's going to be exponential growth. And we have been provided a formula. N equals N sub O times 1 plus R raised to the T power. And this is the important thing to keep in mind. This N is the final quantity, similar to the account balance after the initial quantity or the principal has been invested. So the two are very, very similar, but we're not necessarily dealing with money per se when we deal with, in this particular case. In this example, I believe it deals with the population of a country. And so what happens if we're given 110 million people, and that's where we're starting. Well, what if it grows at a rate of 1.42% annually? Well, again, we have to put that in the form of a decimal. And the 1, we're going to add it to the 1, and we're going to raise it to the number of years. In this case, what about 10 years? What about 20? Well, at this consistent growth rate, it would go to 126.6 million at 10 years, and in 20 years would be at 145.8 million. So what this formula allows us to do using exponential functions is to consider that exponential growth. It's not just a +2 each year or a +100,000. It is growing in an exponential way, and that's what these formulas allow us to consider. What if it happens continuously? What if it's a 1.42 or 1.42% continuously growth rate? That is a slightly different formula. We still have the original amount, which in this case is 110 million. We're still looking for an end amount, all right, after all the details have been, or the parameters have been applied. But now we're going to use the natural base, and we're going to raise it to k. Now, k and r are basically the same thing. We use a k here to differentiate between, like say, an annual growth rate and a continuous growth rate. And that's really all the difference there. Because it's 1.42% continuously, that is our k rate. Well, technically the k would be in decimal form, 0.0142, and we're going to multiply that rate times t. This allows us to explore the exponential side of this growth. And when you can see, it's not a lot different. We're at 126.7 and 146.1 million, respectively, with 10 and 20 years. All right, so you can go ahead and pause the video and try the guided practice number 6. So hopefully now you've restarted the video and you've hopefully arrived at these answers. If you have any questions, let's walk through it. What if it's a population decline? So now we're dealing with decay. They've given us an initial value of 12,426. It's declining at a rate of 6%, and we want to see what it will be in 5 and 10 years, both annually and continuously. So if it's annual, we don't need the natural base. We can simply subtract 6% from 1. Again, why would we do a subtraction? Because the population is declining. So this is actually going to be a sub 100%. If you can think about it that way. We're going to raise that to 5 here because we're doing t at 5 years, and that's going to be 9,119. So declining at 6% on an annual rate is going from 12,000 plus to a little over 9,000. At 10 years, at that rate, it will drop from a little over 12,000 to about 6,700. You can see the exact amounts there. Well, what about continuously? And if we're going to do it continuously, we need to look at it from an exponential standpoint, and we need this natural base. So 12,426, we're going to use our other formula, raise the natural base to the rate times the years. But notice that I put a little negative in there. Rates of decay are negative. Do not forget the negative. If you do, if you leave it positive, this number is going to go up. All right, we don't want that because we're looking at decline. So at 5 years, it's 9,200, a little over 9,200. At 10 years, it would be a little over 6,800. All right, this last problem was actually a guided practice as well. It deals with the number of cases of chickenpox in the United States from 1980 and 2005. Now, you'll need to look in your book to actually see the chart. I'm not going to replicate that here. But we know, to begin with, we're looking at more of an annual case. So we're going to have a new formula here. N of t equals, it's actually not a new formula, it's just written ever so slightly different because we're dealing with this in the sense of a function, equals n sub o equals 1 plus r to t, where n of t is the number of cases in t years after 1980. Now, if you had the chart in front of you, if you have your book, you do, that's going to be 32.2. Now, that's the number of cases after 1980, according to this chart. where did we actually begin? What was going on in 1980? That's our original number, 190.9. All right, and so then we just have 1 plus r, and it's the rate that we're looking for. The book is asking for us, what is the rate of decline in cases? So we're able to know where we ended, know where we began, and we know how long it took us during this span of time. And from 1980 to 2005 is 25 years. So we plug in 25 for t. Now solving for e is not too bad. For one, we're able to just algebraically divide both sides by 190.9. When you see the 1 plus r raised to the 25th power, you know you can take the 25th root of both sides. So that might look a little crazy, but that's just some crafty calculator work. Thankfully, that is not something that you have to do by hand, but it did remove the radical. All right, and so once you do that, you get a negative 0.069 or a negative 6.9% annual rate of decline in the cases of chickenpox. All right, so now they want us now to predict when it will hit 20,000 cases, or when it will drop below 20,000, I should say. So we have this formula here, and now because we know the rate, we can go back to our original formula, know where we started, know the rate of decline or decay, and now we're curious about how many years. And so what we want to do is actually graph this. All right, I got cut off in my video there, had an unexpected guess. But see, so we have our original formula here. We're able to, now that we've calculated the rate of decay, we can plug that in for r and go back and find out what's going on with t. So the year we can put in y equals 20 because it was measured in the thousands. It was the number of cases was measured in the thousands. So we wouldn't put in 20,000. We want to put in 20. What happens when the cases drop below 20? So we can actually plot y equals 20. So this is y equals 20. This is n of t equals 190.9, 1 minus. You can see it right there. And we simply calculate their intersection point and get 31.55. So basically 32. Add 32 to 1980, and you get around the year 2012 is when we should begin to dip below 20,000 cases. So go ahead and check the guided practice problem. It works through exactly the same way. You can see the graph where I have calculated the intersection point, and hopefully you can work through this one with no problems.